Welcome back. In this lecture, I shall introduce Vapour Compression Refrigeration Systems. The specific objectives of this particular lesson are to introduce Vapour refrigeration cycles, discuss Carnot Vapour Compression Refrigeration System and its practical limitations, analyze standard Vapour Compression Refrigeration System abbreviated as VCRS, compare Carnot system and VCRS, and finally present performance analysis of VCRS. At the end of the lesson, you should be able to analyze Carnot Vapour Refrigeration System and its practical limitations, analyze standard Vapour Compression Refrigeration System, discuss qualitatively the differences between Carnot and Vapour Compression Refrigeration cycles, evaluate the performance of Carnot and Vapour Compression Refrigeration System from known data. Let me give a brief introduction. First of all, what is a vapor cycle? In a vapor cycle, the working fluid undergoes phase change at least during one heat transfer process of the cycle. This is against your gas cycle in which the working fluid does not undergo any phase change. So, in a vapor cycle, whether it is a power cycle or a refrigeration cycle, the working fluid undergoes phase change at least during one process. Okay, that is the definition of vapor cycle. Okay. So, vapor refrigerant cycles can be classified into vapor compression systems, Vapour absorption systems and Vapour jet systems. And among these three, the Vapour compression refrigerant systems are the most widely used among all the refrigerant systems in fact. In a Vapour compression refrigerant system, refrigeration is obtained as the refrigerant evaporates at low temperatures. The system input is in the form of mechanical energy required to run the compressor, hence these systems are also known as mechanical refrigeration systems. Vapour compression refrigerant systems are available to suit almost all applications with refrigeration capacities ranging from few watts to few megawatts. That means this is one of the most versatile refrigeration system. First, let us look at Carnot Vapour Compression Refrigeration Cycle. Let me give a brief introduction to Carnot cycle. The Carnot refrigerant cycle is a completely reversible cycle. That means it is internally as well as externally reversible. It is used as a model of perfection for a refrigeration cycle operating between a constant temperature heat source and sink. This is one thing you must keep in mind. This is a model of perfection for constant temperature heat source and sink. It is used as reference against which the real cycles are compared. Now, let me explain Carnot Vapour Compression Refrigerant Cycle. As you can see here, the Carnot refrigerant cycle consists of four basic components: the compressor, condenser, turbine and an evaporator. And the cycle as shown on the TS diagram here consists of four basic processes. Process 1 to 2 is isentropic compression, process 2 to 3 is isothermal heat rejection, process 3 to 4 is isentropic expansion in the turbine, and finally process 4 to 1 is isothermal heat extraction. Now, if you look at process 1 to 2, this is nothing but isentropic compression. Okay. So, in this process you can see that the inlet at the inlet to the compressor you have a mixture of liquid and vapor. That means at point 1 you have a mixture of liquid and vapor. This mixture of liquid and vapor is compressed isentropically from the evaporator pressure PE to the condenser pressure PC. Okay, so at the exit of the compression process you have saturated vapor at condenser pressure. Okay, so that is the compression process. Next, the isothermal heat rejection process. During this process the working fluid rejects heat to the constant temperature heat sink at a temperature of Tc, that is the condensing temperature, and during this process the working fluid undergoes a phase change. At the inlet to the condenser you have saturated vapor 0.2, and at the exit of the condenser you have saturated liquid. Okay, so that is process 2 to 3, which is isothermal heat rejection process. Next, process 3 to 4, this is what happens in the turbine. This is as I have already said, this is an isentropic expansion process. During this process saturated liquid, that is at 0.3 at condenser pressure, expands isentropically in the turbine, and at the exit of the turbine you have a mixture of liquid and vapor at state 4. Okay. And finally, process 4 to 1 is an isothermal heat extraction process. During this process useful refrigeration effect QE is obtained. Okay. So, this is the cycle of a simple Carnot Vapour Compression Refrigeration System. You can see that in this process heat transfer takes place during process 4 to 1 and during process 2 to 3, whereas work transfer takes place during process 1 to 2 and during process 3 to 4. Now, if you do a simple analysis of the system from first and second laws of thermodynamics, you can write for the cycle the first and second laws are like this. Cyclic integral of dou Q is equal to cyclic integral of dou W, and dou Q is nothing but the heat transfer taking place during the cycle. Heat transfer takes place during process 4 to 1, and this is positive because heat is added to the system, and heat transfer also takes place during process 2 to 3, and this is negative because during this process heat is rejected from the system. So, cyclic integral of dou Q is nothing but Q4 to 1 minus Q2 to 3, and Q4 to 1 is nothing but useful refrigeration effect QE, and Q2 to 3 is nothing but heat rejected in the condenser QC. So, cyclic integral of dou Q is nothing but QE minus QC. Now, cyclic integral of dou W. So, work transfer takes place during process 3 to 4 and during process 1 to 2. During process 3 to 4, the system does the useful work in the turbine. So, this is positive. Okay, and during process 1 to 2, work is done on the system. So, this is negative. Okay, and if you look at the schematic, W3 to 4 is nothing but the work output from the turbine WT, and W1 to 2 is nothing but work input to the compressor WC. So, cyclic integral of dou W is nothing but WT minus WC, which is nothing but minus W net. Okay, where W net is the work input to the system. So, if you substitute these in this first law for the cycle, you find that QC minus QE is equal to W net. Now, what is QC? QC is nothing but negative of heat transfer during process 2 to 3. Since this is a reversible process, you can write this as integral TDS from 2 to 3 with a negative sign. And since this is isothermal process, temperature remains constant at condenser temperature, so T can be taken out. So, integral 2 to 3, integral TDS from 2 to 3 is nothing but TC into S2 minus S3. Similarly, QE, that is the refrigeration effect, is nothing but the heat transferred during process 4 to 1. Again, this is a reversible process, so you can write this as integral TDS from 4 to 1. Temperature remains constant at evaporator temperature TE. So, integral TDS is equal to TE into S1 minus S4. Since processes 1 to 2 and 3 to 4 are isentropic, S1 is equal to S2 and S3 is equal to S4, because the expansion and compression processes are isentropic processes. Now, the COP of the Carnot system is given by COP of the Carnot is given as refrigeration effect divided by net work input, that is QE divided by W net. W net is nothing but QC minus QE, this is QC and this is QE. Okay, and all QE and QC can be written in terms of temperatures and entropy changes, that is QE is nothing but TE into S1 minus S4. Similarly, QC is equal to TC into S2 minus S3. Since S1 is equal to S3 and S3 is equal to S4, these terms get cancelled. So, finally, you find that the COP of the Carnot cycle is nothing but TE divided by TC minus TE, where TE and TC are evaporator and condenser temperatures. That means the COP of a Carnot cycle is a function of operating temperatures only. Now, as I have already explained, COP of a Carnot cycle is a function of heat source and sink temperatures only. COP is independent of the nature of the working fluid. Whatever be the working fluid, the expression for COP of a Carnot system remains same. Between the same heat source and sink, Carnot COP is the maximum possible COP. That is why I said that this is used as a standard for comparison. Okay, and COP of all actual cycles will be less than the Carnot COP. And COP of a Carnot cycle increases as evaporator temperature increases and as condenser temperature decreases. Let me explain this. Okay, so you can see here again I am plotting the Carnot cycle 1, 2, 3, 4 on temperature entropy coordinates. Okay, so for a given condenser temperature, that means I am fixing this condenser temperature, and let us say that I am increasing TE. So what happens when you are increasing TE? You find that QE increases and W net decreases. Okay, and since COP is equal to QE by W net, as TE increases, QE increases, that means the area under 1 to 4 increases, and W net decreases, that means the area 1, 2, 3, 4 reduces. As a result, COP increases as TE increases. And similarly, if you fix TE and reduce, let us say TC, So when you are fixing evaporator temperature and reducing the condenser temperature, QE does not change, QE remains constant, but W net reduces. As a result, again COP increases as condenser temperature reduces. The same thing is shown on a graph. Here I have plotted the COP of the Carnot system versus evaporator temperature for different condenser temperatures. You can see that for a given condenser temperature, as evaporator temperature increases, the COP increases. Similarly, at a given evaporator temperature, as the condenser temperature increases, the COP reduces. Okay, that's what we have seen from the expression. And you can also see that the COP increases rapidly with TE, especially for high TC. That means for when the condenser temperature is high, the rate at which COP increases with TE is high. Similarly, COP increases as condenser temperature decreases. However, at low evaporator temperature, that means in this region, the effect of TC on COP is marginal. So these are the observations we make from the expression for COP of a Carnot cycle. Now, what are the practical difficulties with Carnot refrigerant system? We know that the Carnot refrigerant system gives the maximum COP. Then what is the problem in having a Carnot refrigerant system? There are certain practical difficulties which will prevent us from constructing a cycle which operates on a Carnot cycle. Okay, these practical difficulties are like this. The first practical difficulty is with wet compression. I have mentioned while explaining the Carnot refrigerant cycle that during the compression process, the working fluid at the inlet to the compressor consists of liquid as well as vapor. That means you have to compress a mixture of liquid and vapor. Most of the practical compressors are designed to compress vapor only. So if there is a liquid, this kind of a compression known as wet compression. That means whenever you have liquid at the inlet to the compressor, you call that compression process as wet compression. And most of the compressors are not designed for wet compression. So when there is liquid at the inlet, the compressor may get damaged. Okay, so this is one of the practical difficulties with Carnot refrigerant cycle. Okay, the second difficulty is the extraction of work by expanding saturated liquid in a turbine is not economically justified, especially for smaller systems. We have seen that in a Carnot refrigerant cycle, the expansion process is isentropic. That means we use a turbine and extract work. That's how you get an isentropic expansion process. But what is the work output during this process? If you assume that the process is steady flow process, then the work output of a turbine, specific work output of a turbine, is typically given by, if you are neglecting kinetic and potential energy changes, then you find that work output of a turbine is given by integral VdP. And since you are expanding the liquid, and liquids have typically very small specific volume, so you find that this is very small because of the small value of specific volume. As a result, compared to the compressor work input, the work output of the isentropic turbine is very small. Over and above that, when you consider actual turbine will be different from isentropic turbine because there will be some irreversibilities. So the actual output of a turbine will be much less than the isentropic work output. So if you consider the cost involved in building a turbine and in incorporating a turbine and the work output that you get out of it, you will find that in most of the cases, especially for small capacity systems, it is not economically feasible to use a turbine and to extract work. Okay, so the economic feasibility prevents the use of turbine. Okay, so this is the second practical difficulty with a Carnot refrigerant system. Okay. Of course, the first difficulty, that is the wet compression, can be eliminated by using two compressors. Let me show what is the meaning of that. For example, you can look at the cycle here on TS. Okay, this is TS. Wet compression was something like this. The wet compression can be eliminated if you move this point from this point to the saturated point 1. Okay, then the wet compression is avoided. But you have to achieve the compression process. Now you have to add another compressor. Okay, that means the compression process is split into two parts. Part 1 to 2 is an isentropic compression. Okay, and from evaporator pressure PE to an intermediate pressure PI. And process 2 to 3 is isothermal compression from intermediate pressure PI to condenser pressure PC. Okay, so by using two compressors instead of one compressor, you can eliminate the problem of wet compression. Okay. However, you find that isothermal compression is difficult in practice, and the cost also will go up because you are using 2 compressors instead of 1 compressor. Okay. So, these are the practical difficulties with Carnot refrigerant systems. Now, let us look at Vapour Compression Refrigeration System, which is the system used in practice. This system is a modification over Carnot system, and what are the modifications? The first modification is that the isothermal heat rejection process in the condenser is replaced by isobaric heat rejection. This is the first deviation from the Carnot cycle. Second deviation is that the isentropic expansion of liquid in the turbine is replaced by isenthalpic throttling in a throttling device. Okay, so these are the 2 major differences between the standard Vapour compression refrigerant system and the Carnot Vapour compression refrigerant system. Okay, and this standard Vapour compression refrigerant system is known as Evans-Perkins cycle, or sometimes it is also known as reverse Rankine cycle. Now, let me describe the standard saturated single stage cycle. This is abbreviated as SSS. This stands for standard saturated single stage Vapour compression refrigerant system. First, let me explain this. A standard saturated single stage Vapour compression refrigerant system, the exit conditions of evaporator and condenser are saturated. That is why you have this term saturated here. And the cycle consists of 1 low side pressure and 1 high side pressure. That is why you call it as a single stage cycle. And cycle is internally reversible, and compression is isentropic, and expansion is isenthalpic. Okay. So, now let me show the schematic of the cycle and the cycle on TS diagram. You can see here that this cycle also, that means the standard Vapour compression cycle, also consists of 4 basic components: the compressor, condenser, expansion device or a throttling device, and the evaporator. Okay. So, if you compare this cycle with the Carnot cycle, you will find that in terms of the components, the only difference is in the expansion device. There we were using a turbine, here we use a throttling valve. Okay. And the cycle on TS diagram is shown here. It consists of 4 processes. Process 1 to 2 is isentropic compression, process 2 to 3 is isobaric heat rejection, process 3 to 4 is isenthalpic expansion, and process 4 to 1 is isobaric and isothermal heat extraction. Okay. Now again, if you compare this cycle with the Carnot cycle, you find that here the compression is dry compression because you are compressing only vapor. Okay. So the problem of wet compression is eliminated. But as a result of this, you find that the condensation process or the heat rejection process is isobaric but not isothermal, because during the process 2 to 2 dash the temperature is varying, whereas during the process 2 dash to 3 the temperature remains constant. That means initial heat rejection is an isobaric process but non isothermal process, whereas the rest of the process is isobaric as well as isothermal. Now coming to the expansion process, 3 to 4 is isenthalpic process, and this is shown by a dashed line because isenthalpic throttling process is highly irreversible. So we really do not know the path, we only know the end states 3 and 4. Okay. And process 4 to 1, as I said, is isobaric heat extraction, and if you are using a pure fluid, this is also isothermal. Okay. So this is the standard saturated single stage Vapour compression refrigeration cycle. Now how does this cycle compare with the Carnot cycle? What are the differences? For the same heat source and sink temperature, that means for the same evaporator and condenser temperatures, compared to Carnot cycle, we find that the refrigeration effect of the standard cycle decreases. So how do you show that? This can be shown with the help of the TS diagram. You can see here that 1 2 dash 3 4 is the Carnot cycle, that means this cycle is the Carnot cycle. Okay. Whereas 1 2 3 4, that means this one is your standard Vapour compression refrigerant cycle. Okay. Now what is the refrigeration effect of Carnot cycle and what is the refrigeration effect of the standard cycle, and what is the difference between these two? Okay. Let us write the expression for this. Now if you look at the Carnot cycle 1, 2, double dash, 3, 4 dash, the refrigeration effect is nothing but the area under the curve 4 dash to 1, that means this entire area, okay, this entire area, right. Whereas the refrigeration effect of the standard cycle is nothing but area under process 4 to 1, that means this area, okay. So you find that the refrigeration difference between the refrigeration effect of the Carnot cycle and vapor compression refrigeration cycle is nothing but this area 4 dash C D4, that is area A2, and this area A2 is because of the throttling, and this area A2 is also known as throttling loss. Okay. So in terms of you can derive the expression for this. So for example, the refrigeration effect of the Carnot cycle, as I have already told you, is nothing but heat transfer during process 4 dash to 1. So that is nothing but integral TdS from 4 dash to 1, temperature remains constant. So this is nothing but T into S1 minus S4 dash, which is equal to area E1 4 dash Cg. Okay. And refrigeration effect of the vapor compression refrigeration cycle is nothing but heat transfer during process Q 4 to 1, that is nothing but integral TdS from 4 to 1, that is equal to T into S1 minus S4, that is equal to area E1 4dE. So the difference between the refrigeration effect, that is QE Carnot minus QE vapor compression refrigeration cycle, is nothing but the area D4 4 dash CD, which is equal to H3 minus H4 dash, or this is also equal to H4 minus H4 dash, because H3 is equal to H4, because this is an isenthalpic expansion process. This is nothing but area A2, which we call as throttling loss area. Okay. And if you look at the TS diagram, you find that the throttling loss increases as the evaporator temperature decreases and or the condenser temperature increases. And a practical consequence of this is a requirement of higher refrigerant mass flow rate for a given capacity. Okay, because you are losing refrigeration effect, if the capacity is fixed, to get the same capacity, more amount of refrigerant has to circulate. Okay, so this is the consequence of changing the expansion process from isentropic expansion to isenthalpic expansion process. Okay. Now let us look at the heat rejection. You find that for the same heat source and sink temperatures compared to Carnot cycle, the heat rejection increases in a standard vapor compression refrigeration cycle. Again, with the help of the TS diagram, this can be shown very easily. For example, if you look at the TS diagram, again 1 2 dash 3 4 dash is your Carnot cycle, and 1 2 3 4 is your standard vapor compression refrigerant cycle. And what is the heat rejection in the Carnot cycle? Heat rejection in the Carnot cycle is nothing but heat rejected during process 2 dash to 3, that is nothing but area under 2 dash to 3, which is equal to Tc into S2 dash minus S3, that means this entire area. Okay, that is area E2 dash 3 CE. Now what is the heat rejection in standard vapor compression refrigerant cycle? That is nothing but heat rejected during process 2 to 3, that is nothing but the area under curve 2 to 3. Okay, that means this area plus this area. Okay, so this is equal to area E2 3 CE, that is area E2 3 CE, right, the entire area. So you find that the difference between the heat rejection of a vapor compression cycle and the Carnot cycle is nothing but this area 2 dash 2 double dash, or area A1. Okay, and this area is known as superheat horn. Okay, and this is coming because of the fact that we are replacing the isothermal heat rejection of the Carnot cycle by an isobaric heat rejection process. Now because of the differences in refrigeration effect and heat rejection rates, you find that the compressor work input increases when you change over from Carnot cycle to standard vapor compression cycle. Again, with the help of TS diagram, we can show this one. If you look at again the TS diagram, you find that the net work input of Carnot cycle is nothing but QC minus QE of Carnot cycle, that is nothing but area 1 2 double dash 3 4 dash 1, that means this area. Okay, whereas the net work input of a vapor compression refrigeration cycle is nothing but QC minus QE of vapor compression refrigeration cycle, that is nothing but this area, that means area 1 2 3 4 dash C D4. Okay, that means this area plus this area plus this area. Okay, so you find that the difference between the net work input of a standard cycle minus Carnot cycle is nothing but this area, that means the area rectangular area 1 2 dash 3 4 dash plus superheat horn area A1 plus throttling area A2. Okay, that means the difference is nothing but area A1 plus area A2. Okay, this area and this area, right. So as a result of this, so you find that when you have moved away from the Carnot cycle, you lost refrigeration effect, and you also have to spend more amount of work input. Okay, so as a result, obviously the COP of the system decreases. So you find that the COP of the standard cycle is always less than the COP of the Carnot cycle. Okay, you can write this expression. For example, COP of the vapor compression refrigerant cycle is defined as the refrigeration effect of the vapor compression refrigerant cycle divided by the net work input in the vapor compression refrigerant cycle, and QE vapor compression refrigerant cycle is written as QE Carnot minus throttling area A2, and work input of the standard cycle is given, it can be written as work input to the Carnot cycle plus superheat horn area A1 plus throttling area A2. Okay. Now we can define what is known as the cycle efficiency eta subscript R. This is defined as the ratio of COP of standard vapor compression cycle to that of Carnot COP, right. That means cycle efficiency eta R is given by COP of standard vapor compression refrigerant cycle divided by Carnot COP. So that can be shown to be equal to, here if you take QE Carnot by W Carnot as common, then this can be written as 1 minus area A2 divided by QE Carnot divided by 1 plus area A1 plus area A2 divided by W net of Carnot. You find that this is always less than 1 because area A2 is always greater than 0 and area A1 and area A2 will also be greater than 0. Okay, so as a result, cycle efficiency will always be less than 1. So the cycle efficiency, sometimes it is also called as second law efficiency. This is a good indication of the deviation of the standard vapor compression refrigerant system from Carnot cycle. Unlike Carnot COP, the cycle efficiency depends very much on the shape of temperature entropy diagram, which in turn depends on the nature of the working fluid. We have seen that the COP of a Carnot system is a function of the heat source and sink temperatures only, and it is independent of the nature of the working fluid. Okay, but you find that the COP of a standard vapor compression refrigerant cycle also depends upon the shape of the vapor dome on TS diagram, that means which in turn depends upon the nature of the working fluid. Okay, how is it? Let me explain that with the help of the TS diagram. Okay, so as I have already explained to you, here the standard vapor compression refrigerant cycle is given by 1 2 1 2 3 4. Okay, and neglecting kinetic and potential energy changes across the compressor, compression process is 1 to 2. Okay, so if you apply energy balance for the compression process, you find that the work input to the compressor W1 to 2 of the vapor compression refrigerant cycle is nothing but H2 minus H1. That means the enthalpy difference across the compressor, which is nothing but work of compression. Okay, so what I do here is I subtract and add HF, where HF is nothing but the saturated liquid enthalpy at evaporated temperature. Okay, so I am writing H2 minus H1 as H2 minus HF minus H1 minus HF. Okay, now I make one small assumption here. I assume that the saturated liquid line, okay, this is a saturated liquid line, this coincides with the isobar PC. Okay, that means if I extend the isobar in the liquid region, I assume that this isobar coincides with the saturated liquid line. This is a reasonably good assumption because if you look at the actual TS diagram, you find that the isobars are very close to the saturated liquid lines. Okay, that means the process 2 to F is an isobaric process at pressure PC. Okay, and using the thermodynamic relations, TDS is equal to DH minus VDP, and if you apply this thermodynamic relation to the process 2 to F, you will find that this is equal to DH because DP is equal to 0 because this is an isobaric process. So TDS is equal to DH, right, when P is equal to constant. So what is DH here? DH is nothing but H2 minus HF, right. So H2 minus HF, that means this quantity is equal to integral TDS. Okay, integral TDS is nothing but area under the process 2 to F, that means this entire area, okay, this entire area, right, that is equal to H2 minus HF. Now what is H1 minus HF? H1 minus HF is nothing but area under the curve 1 to F. Okay, 1 to F is an isobaric process, so this is nothing but again H1 minus HF is equal to integral TdS, temperature remains constant, so H1 minus HF is nothing but area under curve 1 to F on TS diagram, which is equal to this rectangular area, okay, this rectangular area, right. So you find that under this assumption H2 minus H1, which is equal to H2 minus HF minus H1 minus HF, is nothing but this area, okay, right. So this area is nothing but the rectangular area plus the superheat horn area plus this area A3, okay. And in the previous slides we have seen that for a vapor compression refrigerant cycle, the net work input is equal to this rectangular area plus this superheat horn area plus the throttling area A2. So if you compare that one with this area, which both of them have got to be equal, this will show that area A2 is equal to area A3, okay. The area A2 is approximately equal to area A3, approximately equal to area A3 because here I am making an assumption that the isobar coincides with the saturated liquid line, okay. Now this area A3 depends very much on the shape of the TS diagram, okay. Now depending upon the shape of saturated curves on TS diagram, refrigerants can be classified into type 1 refrigerant, that means ammonia, carbon dioxide and water, type 2 refrigerants, for example CFC11, CFC12, HFC134A, and type 3 refrigerants, that is CFC114, CFC115, isobutane, okay. So let me show these types on TS diagram and what is the meaning of that. You find that type 1 refrigerant has a TS vapor dome like this. You can see that the vapor dome is almost symmetrical, okay, and the type 1 refrigerants are ammonia, carbon dioxide and water, etc. Since the vapor dome is symmetric, you find that the losses due to superheat horn and losses due to throttling both are of the almost same magnitude, that means both are important, right, for type 1 refrigerants. Now type 2 refrigerants, that means R11, R12 and R134A, you find that the loss due to superheat horn is much less compared to the loss due to throttling, okay, because this area is much less compared to this area. Now type 3, that means refrigerants, high molecular weight refrigerants such as R114 and R115 have a peculiar vapor dome, and here you find that there is no superheat horn at all, because the slope of the vapor saturated vapor curve is such that when you start compression with a saturated vapor, the exit of the compression lies in the two phase region, okay. So that means there is no superheat horn, that means there is superheat loss due to superheat horn is non-existent for this type of refrigerants, whereas the loss due to throttling is quite considerable, okay. So depending upon the type of the refrigerant and depending upon the vapor dome shape on TS diagram, you can classify the refrigerants. And what is the use of this classification? You know where you are losing, okay, and if you want to do some modifications, you know where you have to concentrate, okay. Now let us quickly look at the differences between superheat and throttling losses. I have mentioned that because you have changed over from Carnot cycle to vapor compression refrigerant system because of some practical difficulties, two additional losses have been introduced, and the first loss is because of the superheat and the second loss is because of the throttling loss. Now let us look at these losses, okay. If you look at the superheat loss, increases only the work input, it does not affect the refrigeration effect, and as I said, it does not affect refrigeration effect. And in heat pumps, superheat is a part of the useful heating effect. That means if you are using the refrigerant system for heat pumping, that means if you are interested in the heat rejected in the condenser, then you find that the heat loss in the superheat due to superheat horn is not a loss at all, because that can be recovered, okay. Now if you look at the throttling loss, the throttling process is highly irreversible, and you find that because of the throttling process the work input increases, and also the refrigeration effect is reduced. Okay, so if you look at the expression for COP, the numerator reduces and the denominator increases. Okay, so you lose on both sides. So in this respect, throttling loss is more serious compared to, or it has more significant effect compared to the superheat loss. Okay. Now let us look at a simple analysis of a standard vapor compression refrigeration cycle, and this analysis is carried out under the following assumptions. We assume that all the processes taking place in each component is a steady flow process, and we neglect kinetic and potential energy changes across each component, and there are no heat transfer or pressure drops in connecting pipelines, and the analysis is carried out by applying steady flow energy equation to each component. So let me show the analysis for each component. First let us take the evaporator. Remember that the evaporator process is given by process 421. Okay, so if you look at the TS diagram, okay, so this is 1, 2, 3, 4. So process 421. So at the inlet to the evaporator you have a mixture of liquid and vapor, and at the exit of the evaporator you have saturated vapor. Okay, and m dot r is the mass flow rate of the refrigerant, and q dot e is the refrigeration capacity of the evaporator. So if you take the control volume across the evaporator and if you apply the steady flow energy equation, since we are neglecting the kinetic and potential energy changes, you find that the refrigeration capacity q dot e is nothing but mass flow rate of the refrigerant multiplied by the enthalpy difference H1 minus H4. Okay, and the pressure at which the evaporator operates is nothing but the saturated pressure corresponding to the evaporator temperature T. Okay, so if you know the saturation pressure temperature characteristics, and if you know the evaporator temperature, you can calculate what is the evaporator pressure. Okay, and you can, if you know the mass flow rate and the enthalpy difference, you can also calculate what is the refrigeration capacity. Now this parameter H1 minus H4 is known as specific refrigeration effect, and the units are kilojoule per kg. Okay. Now if you apply the steady flow energy equation to the compressor, remember that we are assuming the compression process to be isentropic, so there is no heat transfer, Q is 0. Okay, again we are neglecting delta KE and delta PE, both are negligible. Okay, and refrigerant enters at state 1 at evaporator pressure and temperature, and it exits at state 2 which is at condenser pressure and at a discharge temperature T2. Okay, and W dot C is the power input to the compressor. So if you again apply the steady flow energy equation, you find that the power input to the compressor W dot C is nothing but m dot R into H2 minus H1, where H2 minus H1 is the enthalpy rise across the compressor, and this H2 minus H1 is known as work of compression, and it has units kilojoule per kg, whereas the power input, as you know, is in the units of kilowatts. Okay. Similar to evaporator, you can also take control volume across the condenser. Again there is no work transfer here, W is 0, and delta KE and delta PE are negligible, delta KE is 0 and delta PE is 0. Okay, and Q dot C is the heat rejection rate from the condenser, and heat rejection is taking place at a condensing temperature of Tc. Okay, and the condenser pressure Pc is nothing but the saturation pressure Psat corresponding to this temperature Tc. One thing you must keep in mind is that temperature T2 is not equal to Tc, whereas temperature T3 is equal to Tc. Okay, so this temperature T2 is always greater than Tc because of the de-superheating in the initial portion. Okay, so you can find out the condenser pressure if you know the saturation pressure temperature characteristics, and the heat rejection rate Q dot C can be obtained by this equation. This is from the steady flow energy equation. Q dot C is nothing but m dot R into H2 minus H3. Now if you take the expansion device, expansion process is a throttling process, that means it's an isenthalpic process, and if you take the control volume far downstream of the expansion device, then delta KE will be 0 and delta PE also will be 0, and there is no work interaction, W is 0, and there is no heat interaction, Q is 0. So you find that from steady flow energy equation, H3 is equal to H4, or this process is isenthalpic process. Now, what is the state of the refrigerant at the inlet of the throttling device? This is saturated liquid, right? Saturated liquid at condenser temperature. Whereas state 4, if you look at the TS diagram, is a mixture of liquid and vapor. Okay, so this is a mixture of liquid plus vapor at condenser temperature, at evaporator temperature and pressure. Okay, so you can write the enthalpy at H4 in terms of the saturated liquid enthalpy at evaporator temperature and saturated vapor enthalpy at evaporator temperature and the quality or dryness fraction X4. Okay, so H4 is nothing but 1 minus X4 into HFE plus X4 into HGE. This can also be written as HF plus X4 into HFG, where HF is nothing but HFE, that is the saturated liquid enthalpy, and HFG is nothing but latent heat of vaporization at evaporator temperature. Okay, and H4 is equal to H3, right? So H3 is known because this is nothing but the saturated liquid enthalpy. So H4 is also known because H3 is equal to H4, and HFE and HGE are nothing but saturated liquid and vapor enthalpies at evaporator temperature. So they can be obtained from the properties. So using this expression we can find out what is the quality of the refrigerant at the exit of the expansion device. Okay, so that is the use of this equation. Now finally the COP of the SSS cycle is given by Q dot E divided by W dot C. Right. So Q dot E is nothing but the refrigeration capacity, which is equal to M dot R into H1 minus H4 divided by M dot R into H2 minus H1. So this M dot R get cancelled. So finally you find that COP of the standard saturated cycle is given by H1 minus H4 divided by H2 minus H1, where H1 minus H4 is nothing but your refrigeration effect, and this is nothing but your work of compression. Okay, so finally COP is expressed in terms of enthalpies only, right? And at any point in cycle, the mass flow rate M dot R can be written in terms of volumetric flow rate V dot. V dot is volumetric flow rate in meter cube per second. Okay, and V, small v, is a specific volume in meter cube per kg. Okay, so V dot divided by V becomes kg per second, which is nothing but the mass flow rate of the refrigerant. Now if you apply this equation to compressor inlet 1, then M dot R is equal to V1 dot divided by V1, where V1 dot is nothing but the compressor displacement rate. That means V1 dot is compressor displacement rate, right? This is again meter cube per second, and V1 is nothing but the specific volume of the refrigerant at the compressor inlet. Okay. Now what we do is we write the refrigeration capacity, which is equal to mass flow rate into H1 minus H4, which is nothing but your refrigeration effect, right? And the mass flow rate is written in terms of the volumetric flow rate at the compressor inlet V dot 1 and the specific volume of the refrigerant at the compressor inlet V1. Okay, so Q dot E is written as V dot 1 into H1 minus H4 divided by V1. Now this parameter H1 minus H4 divided by V1 has the units of kilojoule per meter cube. Okay, and this parameter is called as volumic refrigeration effect. Okay, and the units are kilojoule per meter cube. So what is the practical significance of this volumic refrigeration effect? This is an indication of the size of the compressor. Okay, so higher the volumetric refrigeration effect, smaller will be, for a given capacity, higher the volumetric refrigeration effect, smaller will be the required displacement rate of the compressor. Okay, so this is an important performance parameter. Similarly, the refrigeration effect, which has the unit of kilojoule per kg, is an indication of the required mass flow rate. Okay, because for a given capacity, mass flow rate is nothing but Q dot E divided by refrigeration effect. So higher the refrigeration effect, smaller will be the mass flow rate of the refrigerant. Okay. Now we have seen that the most of the properties, that means most of the performance parameters like refrigeration effect, work of compression, COP, volumic refrigeration effect, they are all expressed in terms of enthalpies. So it is really useful to use a pressure enthalpy chart in place of a temperature entropy chart. Okay, this pH diagram is sometimes known as Mollier diagram. So this is very widely used in refrigeration cycle analysis, because using this cycle you can straight away calculate the required performance parameters. Okay, so that is what is mentioned here. Since various performance parameters are expressed in terms of enthalpies, it is very convenient to use a pressure enthalpy chart for property evaluation and performance analysis. Using pH charts, one can easily find system performance from known values of evaporator and condenser temperatures. Let me show this pH chart. Okay, so this is a typical pH chart. Okay, so here the x-axis is enthalpy and y-axis is pressure. Okay, normally the pressure is drawn on a semi-log plot. This is drawn on semi-log plot so that at the lower temperatures this plot opens up. Okay, so generally this is drawn on log scale, whereas the enthalpy is on a linear scale. Okay, so this is normally LNP versus this thing, and this is the saturation. This is the vapor dome. Okay, you have the critical point here, and from this point to this point is your saturation liquid line. Okay, and from this point to this point is your saturation vapor line. Okay, so this is your subcooled liquid region. Okay, and this is your liquid plus vapor two-phase region. Okay, and this is your superheated vapor region. Okay. Now on the pH diagram, obviously the enthalpy constant enthalpy lines are vertical lines, and constant pressure lines are horizontal lines. Okay, and the isotherms, for example, isotherm at evaporator temperature, it is almost vertical in the subcooled liquid region, and it becomes horizontal in the two-phase region, and again it becomes inclined. Okay, and it goes like this, and it again becomes almost vertical at low pressure region, because the pressure is reducing in this direction. When the pressure is low, you find that the isotherm, shape of the isotherm in the superheated region becomes almost vertical. Why is it so? Because when the pressure becomes very small, the vapor starts behaving as an ideal gas. And we know that for an ideal gas, the enthalpy is a function of temperature only. Okay, so if you are fixing the temperature, enthalpy also gets fixed. Okay, so if it is a constant temperature line, then it also has got to be constant enthalpy line. As a result, at low pressure region, the isotherm becomes almost vertical. Okay, so this is isotherm for evaporator temperature, and this is the isotherm corresponding to the condenser temperature. Okay, and this is an isentrope, that means this is a constant entropy line. Okay, in fact you will find that the constant entropy lines will be varying like this. Okay, it will be varying like this. They will be diverging, right? And you can also have constant specific volume lines. On this, constant specific volume lines will be something like this. Okay, if you look at an actual pH diagram, constant specific volume lines and constant entropy lines in the superheated region are also shown in addition to the isotherms in the liquid, two-phase and superheated regions. Okay. Now, how do we represent the standard vapor compression cycle on pH diagram? We know that, for example, if you look at all the four processes, beginning with the compression process, during the compression process, saturated vapor is compressed from evaporator pressure to condenser pressure, and this process is isentropic process. Okay, so if you know this temperature, then you can find out this pressure. Okay, and you can locate this point, right? And you can also find the entropy at this point. Since the compression process is isentropic, you have to go along the constant isentrope, right, along the constant isentrope, and where this constant isentropic line intersects the constant condenser pressure line, that is your exit of the compressor. Okay, so you can draw this process, right. Now process 2 to 3 is nothing but heat rejection in the condenser, and this is we know that is an isobaric process. So all that you have to do is you draw a horizontal line beginning with point 2, okay, and where it intersects the saturated liquid line, that is the exit of your condenser. Okay, so process 2 to 3 is nothing but a horizontal line on pH diagram, and process 3 to 4 is nothing but isenthalpic throttling process. During this process pressure drops from PC to PE and the enthalpy remains constant. So this process is nothing but a vertical line on pH diagram. Okay, and finally the evaporation process, the heat extraction process is isobaric. So it's a constant, it's a horizontal line on pH diagram. So the process 4 to 1 is given by this horizontal line. Okay, so finally you find that the vapor compression refrigeration cycle takes this shape 1, 2, 3, 4. Okay, so you can, once you know the condenser pressure and condenser evaporator pressure or condenser temperature and evaporator temperature, you can easily locate these points, right, and you can draw the cycle on pH diagram. Once you have drawn the cycle on the pH diagram, the calculations become very simple. For example, I want to calculate, I want to find out what is the refrigeration effect. Refrigeration effect, as you know, RE is the refrigeration effect, is nothing but H1 minus H4. Okay, this is nothing but this enthalpy minus this enthalpy, or this is nothing but this. Okay, this is your refrigeration effect. Okay, and what is the work of compression? Work of compression is nothing but H2 minus H1, that is nothing but this enthalpy minus this enthalpy, that is nothing but this. So this is your work of compression. Okay, so the moment you locate all the points, you can straight away read the enthalpy values and you can get the refrigeration effect and work of compression. So COP, as you know, is nothing but RE divided by WC, that means this length divided by this length. Okay, so straight away you get the value of COP, and you can also find out the required mass flow rate, etc., if you know the capacity, because mass flow rate is nothing but refrigeration capacity divided by RE, and RE is nothing but this length. Refrigerant capacity is given, so you can find out what is mass flow rate. And if you read the specific volume from the pH chart, then you can also find out what is the required volumetric displacement at this point. Okay, so like that, using the pH diagram, you can find all the required performance parameters. Okay, so that is the reason why we use these pH charts very widely in refrigeration cycle analysis. Okay, so in the next lectures we will be using this to evaluate the performance of standard vapor compression refrigerant cycles. Okay, and as I have already mentioned, this pH chart is sometimes known as Mollier diagram. Okay. Okay, so let me conclude this lesson. What is that we have learned in this lecture? In this lesson, the Carnot refrigerant cycle and its practical limitations are discussed. The standard vapor compression refrigerant system is introduced and its working principle is explained, and we have compared the vapor compression refrigerant system with Carnot system, and we have seen what are the deviations and what are the consequences of these deviations. And we have presented a simple performance analysis of a standard vapor compression refrigerant system by applying steady flow energy equation to each component. And we have also presented the cycle on a pH diagram, and I have also explained how to evaluate the required performance parameters using the pH diagrams from the known values of evaporator and condenser temperatures. Okay, the performance of standard vapor compression refrigerant system and modified vapor compression system will be discussed in next lectures. Okay, thank you. Welcome back. This lecture is a continuation of last lecture, wherein we introduced vapor compression refrigeration systems and we discussed saturated single stage standard cycle, that is SSS cycle, and we compared the performance of that cycle with an ideal Carnot vapor compression refrigeration system. And we have also given some basic equations for evaluating the performance of this system. So we will continue in this lecture starting with the performance aspects of SSS cycle, and we will also discuss the various modifications to the standard cycle. So the specific objectives of this particular lesson are to discuss the performance of SSS cycle, introduce subcooling and superheating, discuss vapor compression refrigeration system with liquid suction heat exchanger, discuss effect of superheat on system performance, discuss the differences between theoretical and actual cycles, and discuss a complete vapor compression refrigeration system. So, at the end of this lesson, you should be able to evaluate the effects of evaporator and condensing temperatures on the performance of a SSS cycle, evaluate the effects of subcooling and superheating using TS and PS diagrams, evaluate the performance of modified vapor compression refrigeration system with liquid suction heat exchanger, and find whether superheating increases COP or not using a simple criteria, and discuss various irreversibilities in actual systems and their impact on performance. So, let us begin with the performance of SSS cycle. The performance can be obtained from the simple analysis presented in the last lecture and using suitable property data. And typical performance trends show the effects of evaporator and condenser temperatures. What is normally done is we keep the condenser temperature constant and vary the evaporator temperature and find different performance parameters. Then you keep the evaporator temperature constant and vary the condenser temperature. So, in that manner you can find out the effect of both condenser as well as evaporator temperature on different performance parameters of interest. Okay, let me show now the effect of these temperatures on different performance parameters. The first one is the effect of these temperatures on specific and volumic refrigeration effects, and then specific and volumic works of compression, then system COP. So, first let me show the effect of the temperature on refrigeration effect. So, this QE is a specific refrigeration effect. As you can see, it has unit of kilojoule per kg, and QV is volumic refrigeration effect. That means refrigeration effect per meter cube of refrigerant flow. And you can see here that on x axis I have evaporator temperature, and I have got these performance parameters for different values of condenser temperature. So, you can see that condenser temperature is increasing in this direction for specific refrigeration effect, and it is increasing again in the same direction for volumic refrigeration effect. So, from this graph you can easily see that as you are increasing the evaporator temperature for a given condenser temperature, there is a marginal increase in specific refrigeration effect. Okay, and the specific refrigeration effect also increases as condensing temperature decreases. Okay, that means QE increases as TE increases and TC decreases. But as I said, this effect is not very large, it is marginal. That you can easily find out from this pH diagram. As I have already discussed in the last class, this is your refrigeration effect, or this is your QE. Okay. So, if you are keeping the condenser temperature constant and if you are varying the evaporator temperature, for example, I am increasing the evaporator temperature, that means this line shifts up. Okay. So, and you have the new cycle like this. So, what is the increase in refrigeration effect is very small. You can see, and you can see that it